Today we'll be talking about a new feature called Ray Direct Transport, which is in alpha in Ray 2.51.1. I'm Stephanie. I'm one of the creators of Ray, and here today I also have Qiaolin. So we're both software engineers at Anyscale on the Ray core team. We're very excited to tell you about this new feature that we've built. So just a quick outline for this talk. We'll go through why we decided to build this feature. We'll go through a deep dive of how it actually works. And we'll also talk about some of the use cases for RDT, including reinforcement learning for LLMs and heterogeneous training. So you may know Ray today as being this kind of very flexible orchestrator for distributed GPUs. It lets you kind of programmatically orchestrate distributed GPU programs or applications. And one of the kind of recent use cases that we've seen for Ray is this use case in reinforcement learning, or RL for LLMs. And this is a pretty challenging use case to build today. It requires composing across different training and inference engines. So you can imagine here, what we're going to do in RL is actually generate data online using the model itself. So that means that we have to run both an inference engine and a training engine, and these are going to share a copy of the same model. Now, these systems today are supported by different backends. So you can think of things like VLM for inference or deep speed for training. And the loop is more complicated than just this. So we have to use the inference engine to generate some data. We're going to simulate those actions in some environment and get back some reward that tells us how good those actions were. To coordinate all of these things together, we need some kind of controller program that specifies what the RL algorithm looks like and how data and control should flow between these different components. And that's what Ray is really useful for. On top of that, we also have to implement kind of a diverse array of different placement strategies. So you can imagine if you have some cluster of GPUs, there's a lot of different options for how you should place your training and inference engines. And then finally, there's pretty significant data transfer happening here. So in between the training and inference engines, you have to both synchronize the weights for that model, and you also have to pass the rollout data from your inference engine to your training engine. Now, although Ray makes this kind of system very easy to build, in the past, we've also had some significant limitations for building this kind of workload where you're doing a lot of large data transfers between GPUs. And the reason for that is basically because of how Ray's object store is built. So just to give a high-level picture of what this looks like, in RL, you have many use cases that look something like this, where you have a tensor in GPU memory on actor A, and you're trying to send it to actor B, which is on a different GPU. Now, the way that you would do this in Ray previously, and still today, is you can send it through the Ray object store. But the problem here is that the Ray object store lives on CPU memory, and that requires a copy from GPU to CPU memory and back again. If you're on different nodes for actors A and B, that also requires transfer over TCP. So with RDT, what we would like to do is instead enable something like this, where you can have actors talk directly with each other using technologies like RDMA. And by doing this, we can speed up the data transfer for these kinds of GPU workloads by up to 1,000x. And so today we'll talk about how we do that. So we built RDT for applications specifically that need two things. One is they use lots of large objects. And when you have lots of large objects, you really want to minimize any kind of software overheads that come from this kind of unnecessary data copy or serialization, deserialization. And so for RL, for instance, you can think of the weight synchronization process where you have to transfer potentially like gigabytes or even terabytes of data over the network. The other important thing is if you want to use some kind of specialized data transport. So today with AI clusters, there's kind of a variety of different data transports that you could use. And many of these rely on kind of these high-speed networks like InfiniBand. And so what we would like to do is allow Ray users to leverage these kinds of networks. And so the idea behind RDT is to let you use kind of the typical Ray core API of actors, tasks, objects, but now let you choose your own data transport so that you're not kind of limited to just the Ray object store. Okay, so next we'll go into a deep dive showing the API and how this works under the hood. So the key benefits of the RDT API is first that we're going to keep data unserialized in GPU memory. So we'll store data directly at the actors without copying them until we need to. It also lets you pick your own data transport. And meanwhile, Ray is still going to manage kind of all of the control plane aspects, like coordinating data transfers and garbage collection and so on. Today, this supports Ray actors, so actor-to-actor data transfers. It supports torch tensors, which can be nested inside of other Python data. So you could transfer, for instance, a dictionary of multiple torch tensors. And today we're supporting 3 different transports. Gloo for CPU communication, that can be really useful for debugging and development. We also support Nickel and Anyscale, which are 2 libraries from NVIDIA for GPU-GPU communication. One note is that RDT objects act slightly differently from normal Ray objects in that they are mutable. Because what's happening here is that Ray is copying the data returned by a Ray actor by reference instead of by value, so that we can avoid that kind of unnecessary data copy. This does mean, though, that this is different from Ray's object store, which always copies the data by value, meaning that once your kind of actor task is done, it's always safe for the user code to write to that same tensor again. So we also have a kind of API to let you wait until Ray has actually freed the object, and then you can safely write to a tensor again. Okay, so now let's talk about the transport options. So out of the box, RDT supports 2 kinds of transports today. One are collective-based transports. So if you're familiar with collective libraries, the way that this works is that you need to specify your collective group ahead of time. And that lets you, at runtime, then execute kind of these high-performance collective primitives, such as all reduce. You can also use it for point-to-point transfers, which is what we're using it for today. So in this kind of setting, the Ray driver is going to initiate the transfer between those 2 collective actors. We also support NVIDIA Anyscale for one-sided transport. And what this means is that instead of having to have the sender and receiver both execute the transfer at the same time, in this case, it's one-sided, meaning that either the sender or the receiver can initiate the transfer on their own. And so in this case, we support 2 kinds of patterns. One is the case where you have a Ray driver kind of coordinating the transfer, and the other case is a sort of direct Ray.put on one actor and then a Ray.get on another. So let's see what this looks like. First, looking at collective transports. So this is kind of a standard Ray program where we're creating 2 GPU actors, sending or submitting a task on one, and then sending the result to another. And here, that first task returns a torch tensor that lives in GPU memory. So the way to enable RDT is, in this case, we have 2 steps for collective transports. So first, we need to add this Ray.method decorator to the actor task that returns a GPU tensor. And that tells Ray basically not to copy this data into the object store, but instead to keep it in the actor's memory. And the second step, because this is a collective transport, is that we also have to declare the collective group ahead of time to Ray. And so we do that before executing any tasks. For one-sided transports, we only need to do that first step, because any actor can sort of initiate a transfer with any other actor. And we also offer the second option of using a Ray.put API. So what that looks like is very similar. Instead of decorating the Ray actor method, we decorate the Ray actor class, saying that this actor class is going to enable using Ray.put with a tensor transport. We extended Ray.put with this tensor transport hint, saying that the data should be passed using Anyscale. And then the Ray.get call looks the same. So next, I'll hand it over to Qiaolin, who will walk you through how this actually executes.
Yeah, now let's try to understand RDT on the hood. So we can see in this example, it has actor A and actor B, and we try to run a random function on actor A and the sum function on actor B. So if you enable RDT, each actor will have a GPU memory object stored on the GPU, and first is the driver will recurse the RDT object reference. In that case, because we are using NCCL, so it will recurse the tensor transport as NCCL. And the driver will try to run random function on actor A. It will extract and register tensors into the GPU memory object store. Then the actor A will return the metadata of the tensors to the driver. Usually the metadata is a shape of tensors, and because we are using NCCL here, so it will also include the NCCL specific metadata like the NCCL descriptors. Then when we try to run some function on actor B, the driver will send the metadata of the GPU objects to the actor B, and after that, we can initialize the transfer from actor A to actor B through RDMA. Then the actor B will load the tensors from the GPU memory object store, then execute the sum function. So for the GC, firstly, we will do the GC on actor B to GC the local copy after task finishes. And then when we execute the line of delete T reference, the reference counter of the T reference will go to 0, and the driver will GC the metadata. Then it will try to run GC for actor A to GC the primary copy. And for the radial pull and radial get, it's very similar with the previous example. The actor A will, when actor A runs the function random, it will extract and register the tensors into GPU memory. And then we will get the reference, and it will send the metadata to actor B. When actor B tries to run radial get, it will initiate the RDMA transfer from actor A to actor B, and then the actor B can get the data. And here's the benchmark for the RDT. We can see for larger data size, RDT can achieve over 1000x performance improvements than array object store, because RDT doesn't need the serialization and deserialization, and it will use a GPU to GPU direct memory RDMA to transfer, and it's much faster than the TCP transfer.
Cool. And then we'll finish up with just showing some use cases for how you can actually use this API. Back from the beginning of this talk, we talked about how Ray can be used to orchestrate these data flows across GPU meshes. So we already talked about this RL for LLM use case. We're also exploring other use cases like heterogeneous multimodal training. So this, for example, could be a case where you're using different parallelism strategies for different models or different sort of submodels within your larger model. And so we're experimenting with using RDT to actually execute this data transfer, no matter how your kind of actors are placed across GPUs. So let's look first at the RL for LLM use case and just dive one step further into how this can actually be distributed using Ray. So the idea here is that we have this kind of data flow picture, and we can take each of these kind of different components and now distribute them using one or more Ray actors. We can also include things like a replay buffer, which is used in some RL algorithms to be able to learn on past experiences. So you could, for instance, launch one or more replay buffers, each using a Ray actor. And then you can define the kind of high-level RL algorithm using the Ray driver program. And now finally, the last piece is that we can now use RDT to execute the weight synchronization between the training and inference engines using RDMA. Okay, so the way that this will work is that we first have our training loop on the driver. And there are lots of different options for how you can set up your RL algorithm. But in this case, what we're going to do is we're going to launch a generation step So this is going to launch one batch of rollouts using your inference engine. Then we're going to launch a training step in parallel. And so this is a kind of one-step off-policy method where your generation is kind of at most one version behind your training. And then we're going to use ray.get to synchronize your training and inference engines to make sure that the versions don't go out of sync. So that's on the driver side. We can also specify how the weight synchronization should be done. And so the way that that looks is that we can take the learner class. This is returning a reference to its model weights. And we'll add this decorator, the ray.method tensor transport decorator. And that tells Ray that we're going to use NCCL for the weight synchronization. And we did some experiments just using a small model, around tens of megabytes. And this can already lead to pretty significant performance improvement. Okay, so yeah, today we talked about Ray Direct Transport. So this is available in Ray 2.51.1. This is the alpha version. And this can enable up to 1,000x faster GPU-GPU transfers compared to using the default Ray object store. We're also working on some ongoing collaborations with RL projects such as Virl and SkyRL. And we also have a bunch of planned features that are in the pipeline. So that includes things like async I/O support. We're also looking into different transport backends, so backends such as CUDA IPC, as well as making the transport completely pluggable. And then finally, looking at different performance optimizations. This is definitely very much an active project, so we're really excited to hear any feedback that you all have. Yeah, thanks, and yeah, we can take some questions as well. Sorry, we can't really see, so I think there's a hand here. Yeah.
I had a question. So you would use like RDMA if you're like on two different nodes, but if you're on the same node, you would want to use like nickel instead. How would you like switch between? I would want to use nickel like in one node. How would you do that with the ray transport?
Yeah. So actually, the ray. The question I'll just repeat into the mic is basically that you have like all these different kind of placement options. Sometimes you want to use NCCL, maybe sometimes you want to use nickel. Using the RDT API, we're actually, the ray.method, that kind of decorator, it can be specified at actor definition time. It can also be specified at runtime. So if you specify at runtime, this is actually using we're just reusing the standard kind of Ray core APIs that let you override the decorator. And so you can say basically, you can have some logic that says like, if the actors are placed like this, you should use this transport and so on. Yeah. At the moment, we're not looking into trying to do this automatically. We want to make it kind of more explicit right now, but that could be an option in the future too.
I have a question about, do you have plans to extend RDT to also cover the CPU with the object? So basically, in CPU memory, if the object is too large, then serialization and deserialization will be pain. And if we can directly copy, like directly move the data and skip the serialization process, that would be great.
For CPU data, do you mean CPU tensor or other different data?
You guys start with tensor, but in general, say I have a CPU memory data object, say like the half gigabyte, and I don't want to make data transfer across node, but I don't want the serialization and deserialization. So can RDT be extended to cover that case?
Yeah, RDT actually support CPU to CPU tensor transfer. It's the same as a GPU to GPU tensor transfer, but you will use Gloo or NCCL instead of nickel. Yeah, and for other data type, like maybe different data type instead of tensor, we may support it in the future. Yeah.
Right there? Yeah.
About the collective group, is this Ray enabled? I mean, can the collective group be created automatically using some Ray annotation? Why does the user have to do it manually?
Yeah. Right, so the question is, can the collective group be created automatically, and why does the user have to make it explicit right now? Yeah, so you could actually do it implicitly. This is like something that we're also kind of debating, is like how explicit we want to make this API. Right now, we're kind of making it more explicit so that you sort of, as your user, like sort of exactly what's happening when. Because there is a cost also, right? So like creating a collective group is not free. And so we sort of want to make it obvious where that's happening in the user code. Yeah. Are there any other questions?
Quick question.
Oh, yeah.
In the examples, you talk about when you do the trainer and the generator. We also have support for this in, for example, in the racer as well. For horizontal scaling, for example, you can actually also leverage this for spin up new cluster, or even support different stages of your inference. Does this feature also get supported in that type?
Yeah, so this is it's a general Ray core feature, and so actually it's it's our goal to make it kind of helpful for different Ray libraries like Ray Surf. Yeah, I mean, I think if you have use cases like that, we're happy to talk through them more. It sounds like that use case would work, though. Yeah. Sure.
So you give some examples about using the data transfer inside the reactor. So does it also support the rate task?
Do you want to answer? Okay. Yeah. So the question is whether it's supported for Ray tasks. So unfortunately, no, it's not supported for Ray tasks. We're not planning to support that soon. Part of the reason that we're doing it with Ray actors is because we actually are now kind of storing state with the worker, right? So like these GPU tensors, we're storing them inside of the actor memory. So while we could support it for tasks in the future, it sort of breaks the task model where you have, once the task finishes, like we clean up all system state. So at the moment, we're kind of focused more on these actor tasks, especially actors that are kind of stateful in terms of GPU memory.
Do you see any overhead on GPU utilization of GPU memory when this?
Because we will do GC after the reference counter of the objects goes to 0, so I think the GPU utilization will be fun. And in the future, you may also build some features like offload the GPU memory to the CPU. But yeah, it's in our future plan. Yeah.
So are there any story-related inference or failure recovery of say, the GPU time or something?
Yeah, good question. So currently, the failure model is that it depends on which transport you're using. But right now, it's basically that if you're using a collective group, for instance, and one process fails, the collective group is no longer usable. So we destroy the collective group and we just propagate errors. We're working on kind of better error detection in the future, but right now, the kind of ultimate fallback is basically to kill the processes involved. Because many times with these like GPU transfers, if one process fails, the whole thing kind of hangs, which is not great because you also don't get a good error message in that case. So at the moment, the kind of what you might see is that a process will fail, and then Ray will kind of give you the error message saying where this error came from. But it's definitely a kind of active area, or an area where we can do much better, I think. I guess the other thing I should say is that at the moment, we haven't actually tested this with the lineage-based reconstruction in Ray. We don't necessarily have like a solid use case for that yet. But in theory, like this should kind of interoperate sort of well with the existing lineage reconstruction.
I'm not so sure this is applicable, but since you know more than I do, any difference between RDMA and RDMA over converged Ethernet V2 in this scenario?
I think so I guess those were sort of just like different kind of variants of RDMA, and it depends like what your hardware looks like there. I think for what we're trying to do here is kind of be you can think of it as like maybe a middle software layer for these different libraries. At the moment, we're not really kind of solving this problem of like, this is the software library you should use. You sort of have to do that yourself. Yeah. Are there more questions? Oh, yeah.
Last year, you introduced
Compiled graphs? Yeah.
yeah, last year you introduced the graph.
Yeah.
And I think it talks about the same, kind of the same use case, but it has a lot of code from the end user perspective. But I thought it also has a lot of other, enables other kinds of optimization. Wondering where do you see that going?
Yeah, so the main difference between Ray compiled graphs and this API is that the compiled graphs API was built off of the lazy execution in Ray. And so basically the idea there was that, if you have the static graph ahead of time, you can do a lot more kind of optimization on that. I think what we found from kind of working with users is that in a lot of cases, what people really want is just faster data transfer and the ability to bring their own transport. And so that's why we kind of built this. So you will see, kind of compared to compiled graphs, there can actually be some performance overhead here because we have some like control plane operations that we're doing now at runtime versus at compile time. But what we're hoping is basically that the API is kind of like a pleasure to use. And so maybe this is actually okay, especially in cases where the data transfer is the main bottleneck. But yeah, I think still kind of TBD on how these projects will come together in the future.
We haven't done this benchmark. Actually, we just do actor-to-act, one actor to one actor transfer. But yeah, that's a good suggestion. We will try this later.
Yeah, I think at the moment the API is definitely focused the most on point-to-point transfers, which is also sort of the pattern that's easily expressible using the Ray Core API. I think in the future we're also interested in experimenting with APIs that kind of let you abstract away collective communication. But at the moment, we need kind of more API support from Ray Core to express that kind of pattern. Yeah. Is there any more? Oh, yeah.
Does the transportation has to be GPU to GPU, or it can be CPU actors to actors?
Yeah, for Nico, it can only support GPU to GPU, but we also support Gloo and Anyscale, which can support CPU to CPU tensor transfer.
How about in between the two? That ever use case well, we need to, let's say, have a vector on the CPU side, and then you actually want to transfer that.
You mean CPU to GPU? I think Anyscale can handle this.
Yeah, so right now, this is a Ray Core API, and Ray Data and Ray Train are two libraries built on top of Ray Core. If you notice, like we're not making this kind of an automatic thing, mainly because there are also changes in the semantics, right? So now the objects are mutable and so on. So we're definitely interested in integrating with libraries like Ray Train and Ray Data, but it will require some changes at the library level to do that properly. So one example would be that kind of heterogeneous training example that I mentioned. That's a possible collaboration with Ray Train. Yeah. So basically, probably in the future that will happen. Yeah.
So do we have any benchmark for CPU to CPU communication within Gloo and Anyscale? Like I saw the one with GPUs, but do we have any benchmark for CPU to GPU?
Yeah, we also did the benchmark for CPU to CPU transfer for Gloo and the Anyscale CPU. And it's also much faster than the object store because it will not introduce the serialization and the deserialization overhead. And yeah, so you can try this later, but yeah, it's maybe a little slower than the GPU to GPU.
But I was mostly interested between these two actually, between Gloo versus Anyscale. Like
Yeah, I think unfortunately at least I'm not familiar enough with Gloo's implementation to say like off the bat which one would be better. It's hard to say. Yeah, I would say also for CPU to CPU, you should also consider still the Ray object store, which can have like some nice benefits also, especially like if you're kind of on the same node. Yeah.
Just one more follow-up.
Yeah.
You mentioned you supported nested tensors for dictionaries. Like, so in that case, can you directly put the full dictionary of a tensor into the code call of the EA, or you have to look through it and put all of the tensors?
Yeah, right now you would rate.put on the entire dictionary, and then just the tensors would get extracted and put into the RDT store. Yeah. Mhm.
Go ahead.
Okay, I think we're out of. Oh.
See this evolve with the general object store API right now, because it seems like you store a lot of state in single actors. It's almost functioning as a mini object store right now. How do you see like when to use object store, when to use this? Is this API ultimately supplant object store?
Yeah, I would say that I would definitely start with the Ray object store first. The Ray object store is kind of more straightforward to use, right? So it has like the object immutability. It's sort of very clear kind of how much state and how much resources you're using. With this, like I would only use this basically if the data transfer becomes a bottleneck. So you would really want to profile your application and see. Yeah. Okay, I think we're out of time, but yeah, we're happy to stick around a bit longer in case you have any further questions.